For America, the jet age began the night of October 4th, 1941, with the arrival of a top-secret engine at a barren airport in Boston's Back Bay. It was Sir Frank Whittle's turbojet. Built by General Electric on the same grounds that now produce F414 engines for the Navy's Super Hornets, the IA engine was the first jet engine flown for the United States during World War II. Through the Korean and Vietnam Wars, GE began leveraging its military engines to help revolutionize civilian air travel. And in the 1970s, GE's powerful core for the B-1 bomber helped a fledgling Franco-American alliance launch the best-selling engine in aviation history. 40 years later, GE and the Department of Defense are still designing the world's most fuel-efficient and powerful engines. But emerging threats in the Pacific will require next-generation fighters to not only fly twice as far as contemporary combat aircraft, but with unprecedented speed and power. The problem is, today's most advanced combat engines are limited by their fixed-cycle designs, which can achieve either maximum power or fuel efficiency, but never both. Until now, that is. On a chilly November morning in 2013, a group of Air Force and GE engineers cramped into a Cincinnati test cell to witness a demonstration so monumental that it would forever change the accepted limits of propulsion. After 7 years and more than $1 billion in adaptive and hot section technology investment, GE and the Air Force have finished testing the world's first 3-stream adaptive cycle engine. But what is it that makes this radical design so different from a fixed cycle engine?
To kind of put it simply, it's a new architecture that takes the best of a commercial engine and combines it with the best of a fighter engine. So when I need high thrust, I can get high thrust. But when I don't need that high thrust, I can move into a super fuel efficient mode.
The secret lies in what we call variable geometry features, which alter both fan pressure ratio and bypass ratios, the two crucial elements affecting fuel efficiency and thrust.
We can vary the pressure and bypass ratios to optimize performance across the flight envelope. Like in takeoff conditions, we can operate like a conventional fighter airplane in a high pressure ratio, low bypass mode, which allows you to maximize thrust. However, for cruise or loiter conditions, we can pull back to a high bypass ratio, low pressure ratio mode that optimizes fuel efficiency. It really provides the pilot the best of both worlds, from the commercial fuel savings or the military high performance.
The performance advantages of GE's adaptive cycle engine are stunning. A 25% reduction in fuel consumption, a 30% improvement in operating range, and a 10% increase in thrust, all with unprecedented heat-sink capability. But a variable fan on its own isn't enough to deliver these game-changing improvements. Equal credit goes to hot section technologies developed for GE's next-generation commercial aircraft. Heat-resistant ceramics and 3D printed components saw their most aggressive ever deployment in GE's adaptive cycle engine. Limited to static parts in its commercial and advent engines, GE's adaptive cycle engine features the world's first ever rotating CMC blades in the turbine, cutting 2/3 of the weight while eliminating the need for precious cooling air, which can now be diverted elsewhere to make the engine even more fuel efficient. Naturally, there was much interest to see how the advanced hardware performed during these historic tests. And after reviewing the data, the Air Force confirmed that GE's adaptive engine set the record for the highest combined compressor and turbine temperatures in the history of aviation.
Well, I would say overall the hardware is in remarkable shape. There were some distress, but you learn from that. There are some components that look like they hadn't even been running the engine.
The advantages of this futuristic architecture don't end with record power and fuel efficiency. There's a third benefit, aptly named the third stream of air. This extra source of airflow can be used to provide a low-temperature heat sink for the entire aircraft.
The other piece of it is thermal management, which is more and more important on newer and advanced engines. We, the engine, are the heat sink for all of the electronics and heat load that the aircraft needs to get rid of. And with this new third stream, that provides a brand new cooling stream with much more thermal capacity than ever before. So it's really balancing between thermal management, thrust, and fuel efficiency. Those three things you can optimize at different points of the flight envelope, whereas historically you never could.
In the coming years, GE will continue to invest in its suite of adaptive cycle technologies with the hopes of entering service in the next decade. By that point, GE's record investment in advanced manufacturing facilities for its commercial engines will ensure low-risk manufacturing readiness to produce similar parts for the adaptive engine.
There's only been a few major leaps of this kind of change in the history of jet engine development. There was the leap from piston engines to turbojets. There was a leap from turbojets to turbofans. Now we're making the leap from conventional fixed cycle turbofan to a three-stream adaptive cycle engine. We're helping set the architecture and the technologies that are going to be useful for the next 20, 30, 40 years to the warfighter.
One of the things we're very proud of is the partnership that we've established with General Electric in this case. It has developed a significant amount of trust and respect in the relationship, and we end up with a better product that's going to allow better defense of our country ultimately, from an Air Force perspective and a DoD perspective.
If history is any judge, military propulsion engineers at GE and the Department of Defense will have no trouble adapting to that fight.